Our universe is filled with puzzles that defy all explanation. We are about to journey through 25 of the cosmos's most profound secrets, from the invisible forces tearing space apart to the strange signals that hint we are not alone. By the end, you will have a front row seat to the greatest unsolved cases in modern astronomy. Why does the solar system seem tilted off its axis? And what is the true identity of the dark energy accelerating our cosmic fate? What single cosmic mystery do you find the most compelling? Our journey into the cosmos begins with a ghost. This invisible substance, known as dark matter, is the universe's most influential missing person. We know it is there because we can see its powerful gravitational hand at work. Entire galaxies spin so fast that they should fly apart, yet something unseen holds them together with immense, invisible chains. This cosmic glue makes up roughly 27% of everything in existence, far outweighing all the stars and planets we can see. But what is it made of? The leading suspects are exotic particles that barely interact with normal matter. Scientists call them WIMP, which stands for Weakly Interacting Massive Particles. These hypothetical entities would be heavy and only communicate with our world through gravity and the weak nuclear force, making them nearly impossible to catch. Another promising candidate is the Action, a particle so lightweight and feeble it could be streaming through you right now without a trace. The hunt for these phantoms is a story of human ingenuity. To shield their experiments from the constant cosmic chatter of regular particles, physicists have built laboratories deep underground. In abandoned mines and beneath mountains, they operate incredibly sensitive detectors, waiting for the once-in-a-lifetime tremor that might signal a dark matter particle brushing against an atom. So far, the silence is deafening. We are surrounded by an ocean of something we cannot touch, see, or hear, a fundamental presence that sculpts the cosmos yet remains utterly anonymous. While dark matter pulls the cosmos together, an even more dominant and mysterious force is actively tearing it apart. This is dark energy, the universe's most baffling antagonist, and it makes the very fabric of space stretch faster with every passing moment. Its discovery in the late 1990s was a complete shock to astronomers. By carefully studying the light from distant stellar explosions called Type 1, a supernova, which act as cosmic mile markers, two independent teams made a chilling realization. The universe is not just expanding, it is accelerating. The most distant galaxies are fleeing from us at a speed that increases over time, pushed by an unseen repulsive force. The leading, though deeply unsettling, explanation is that dark energy is an intrinsic property of empty space itself. Albert Einstein once proposed a similar idea with his cosmological constant, a mathematical fudge factor he later called his greatest blunder. He introduced it to keep the universe static, but then discarded it when expansion was discovered. Now it seems he may have been right for the wrong reason. This cosmological constant could be a form of energy inherent to the vacuum of space, a constant push that grows stronger as the universe expands and creates more space. If this relentless acceleration continues, it paints a lonely and cold future for the cosmos. Galaxies beyond our own local group will eventually be pushed so far away that their light can no longer reach us. The sky will grow dark and the universe will become a vast, empty, and silent void. This force is not a small player. It constitutes about 68% of all the energy in the cosmos. We are left to wonder, is this acceleration a permanent feature of space, or could it change over eons, perhaps even reversing into a catastrophic collapse? The true identity of dark energy is the central question determining the ultimate fate of everything. Our very existence is the result of a cosmic crime scene. The Big Bang should have created a perfect, balanced universe with equal amounts of matter and its ghostly mirror image, antimatter. For every particle of matter born, an antiparticle should have emerged. The problem is, when matter and antimatter meet, they annihilate each other in a flash of pure energy. If the universe had begun in perfect balance, all of its contents should have mutually destroyed one another, leaving behind a desolate sea of radiation and nothing else. Yet here we are, in a cosmos filled with galaxies, stars, and planets, all made of matter. Something tipped the scales in our favor. This is the mystery of the matter-antimatter asymmetry, a fundamental imbalance that allowed a tiny, 1 in a billion surplus of matter to survive the early universe's great annihilation. That tiny leftover is everything we see today. The search for an answer leads physicists to a subtle phenomenon known as CP violation. CP stands for charge and parity, two fundamental symmetries that physicists long believed were inviolable. Charge symmetry means the laws of physics should work the same if you swap every particle with its antiparticle. Parity symmetry means the universe should behave identically to its mirror image. For a long time, it was assumed nature respected both, but experiments with exotic particles called kaons and later B mesons revealed a tiny crack in this perfect mirror. CP violation is the discovery that certain particle processes happen at very slightly different rates than their antimatter counterparts. It is as if a spinning coin made of matter has a 51% chance of landing on heads, while an antimatter coin has only a 49% chance. This minuscule bias, repeated across the newborn universe, could have been the mechanism that allowed matter to win. The hunt is now on to find larger, more dramatic examples of this symmetry breaking. Experiments at the Large Hadron Collider and other facilities are meticulously comparing the properties and decay rates of particles and antiparticles, searching for any other deviation that could fully account for our material world. We are essentially searching for the fingerprint of the process that made our existence possible, a quest to understand why there is something rather than nothing. Even the most successful cosmic recipe has one stubborn ingredient that refuses to match the predictions. Our understanding of the universe's first few minutes, a period known as Big Bang nucleosynthesis, is a triumph of modern cosmology. The models calculate with stunning accuracy how much primordial hydrogen and helium should have been forged in that initial cosmic furnace, and these calculations match almost perfectly what we observe in the oldest stars and gas clouds. But there is a glaring exception, a single element that breaks the perfect harmony: lithium. The models predict a specific amount of lithium-7, the most common isotope of this light metal, that should be present in the ancient universe. Yet when astronomers look at the oldest stars in our galaxy, they find only about 1/3 of the expected lithium. This is the cosmic lithium problem. It is not a small miscalculation, it is a fundamental discrepancy that suggests a crack in our otherwise solid picture of the early universe. So where did all the lithium go? Perhaps our understanding of nuclear physics is incomplete, and some unknown reaction in the first few minutes destroyed lithium faster than we can account for. Or maybe the models for stellar interiors are wrong, and these ancient stars are somehow burning and depleting their surface lithium over billions of years. Another, more exotic possibility is that an unknown form of dark matter decayed in the early universe, altering the delicate nuclear reactions that produced the light elements. This missing lithium is a small but persistent clue, a single thread that, if pulled, could unravel our entire understanding of the universe's first moments or reveal entirely new physics operating at the dawn of time. Sometimes the greatest mysteries are not found in the distant cosmos, but drifting through our own celestial backyard. The Pioneer anomaly is one such puzzle, a subtle but persistent tug on two of humanity's most distant robotic envoys. After completing their missions to Jupiter and Saturn, the Pioneer 10 and Pioneer 11 spacecraft continued their silent journeys into the void. Yet as they traveled beyond the outer planets, tracking their radio signals revealed something deeply strange. Both probes were experiencing a tiny, unexplained deceleration, a constant sunward pull equivalent to just 10 billion times weaker than the gravity we feel on Earth. It was as if an invisible hand was gently applying the brakes. For decades, this minuscule drift defied all conventional explanation. Was it a sign that our understanding of gravity, defined by Einstein's theory of general relativity, was subtly wrong in the vast, quiet expanse of the outer solar system? Or was the answer far more mundane, hidden within the spacecraft themselves? The most compelling solution turned out to be a lesson in thermal engineering. These probes, powered by radioactive generators, produced a significant amount of heat. Scientists performing painstaking computer simulations realized that this heat was not radiating away from the spacecraft perfectly evenly. A tiny fraction more was emitted from the back of their dish-shaped antennae than from the front. This imbalance created a tiny but constant recoil force, a gentle push from photons of heat itself that perfectly accounted for the anomalous deceleration. It was not a breakdown of physics, but the ghostly nudge of their own warmth. Yet for a time, this mystery opened the door to far more exotic ideas, from the influence of unseen dark matter to modifications of the laws of gravity. The pioneer anomaly serves as a powerful reminder that even in the grand quest to understand the universe, we must first account for the faint whispers of our own creations. Just when we thought we had a clear map of the infant universe, a bizarre alignment emerged that seems to point directly at us. This cosmic oddity is known as the axis of evil, a dramatic name for a pattern discovered in the afterglow of the Big Bang itself, the cosmic microwave background. This ancient light, a snapshot of the universe when it was just 380,000 years old, should be the most random thing we can observe. Its hot and cold spots, tiny variations in temperature, should be scattered across the sky like a random spray of paint. Yet when scientists analyzed this data, they found a spine-chilling correlation. The largest of these fluctuations appear to be aligned, strangely, with the plane of our own solar system. It is as if the universe's earliest structures are subtly pointing toward our local cosmic neighborhood. The statistical chance of this happening at random is astronomically low, so unlikely that it throws a fundamental assumption of modern cosmology into question. This is the cosmological principle, the bedrock idea that the universe is homogeneous and isotropic. In simpler terms, it means the universe should look roughly the same in every direction, and no one place should be special. We are not supposed to be at the center of anything, yet the axis of evil suggests our vantage point might not be so random after all. This alignment could be a terrifying hint that we occupy a privileged position, a thought modern science has worked for centuries to dispel. Or perhaps it is a colossal fluke, a statistical mirage in the data. The most unsettling possibility is that it is a sign of something deeper, a fundamental feature of the cosmos we have not yet grasped, one that connects the largest scales of the universe to our own humble corner of it. This profound silence among the stars presents a puzzle so stark it has its own name, the Fermi paradox. The universe is unimaginably vast and ancient, with billions of planets that could potentially support life. The numbers alone suggest the galaxy should be teeming with intelligent civilizations. So why do we hear nothing but static? This cosmic quiet is one of the most unsettling mysteries we face. One chilling answer is the Great Filter hypothesis. This idea suggests that the evolution of life from its origins to a spacefaring civilization requires passing through a series of incredibly difficult stages. One of these stages, the theory goes, presents a barrier so formidable that almost no species ever gets past it. This filter could lie in our past. Perhaps the spontaneous genesis of life itself is an astronomically rare fluke. Or it could be waiting for us in the future. Maybe the development of advanced technology inevitably leads to self-destruction through nuclear war, engineered plagues, or a runaway artificial intelligence. The terrifying implication is that if the filter is ahead of us, our own civilization may be approaching its own extinction event. Other solutions are less grim but equally mind-bending. Perhaps intelligent life is common, but it evolves into forms of consciousness so alien that communication is impossible. Their thoughts, their technology, their very perception of reality might be as incomprehensible to us as a radio broadcast is to a tree. They could be all around us, embedded in the fabric of space-time or existing in dimensions we cannot access, and we simply lack the senses to notice. Or maybe we are living in a cosmic wilderness preserve, deliberately left alone by a galactic community that observes a strict policy of non-interference. The silence, then, would not be empty. It would be a signal in itself, a message that we are not yet ready to join the conversation. Every time we point a radio telescope at the sky and hear only the natural whisper of the cosmos, we are confronted with the same haunting question. Are we truly alone, or are we just not listening the right way? That profound silence was broken once for just 72 seconds. In the summer of 1977, a radio telescope at Ohio State University known as the Big Ear was performing its routine scan of the heavens. A volunteer named Jerry Amon was reviewing the computer printouts days later, a long scroll of paper filled with numbers and letters representing the faint radio chatter of the cosmos. His eyes locked onto a sequence of characters so unexpected that he circled it in red pen and wrote one word beside it. Wow, this was not just another blip. The signal was a powerful, narrowband burst at exactly the frequency of 1.42 GHz, a radio band that is naturally quiet and protected by international agreement, making it ideal for interstellar messaging. It came from the direction of the constellation Sagittarius, and it matched all the predicted characteristics of a signal beamed from an intelligent civilization far beyond our solar system. For one magnificent minute, it seemed we might not be alone after all. Yet that glorious possibility was followed by decades of frustrating silence. Astronomers have pointed their dishes toward that same patch of sky countless times, scanning across a wide range of frequencies, hoping for a repeat performance. They have never heard it again. The wow signal remains a solitary, brilliant flash in the cosmic dark. In the absence of a repeat, scientists have scrambled for natural explanations. Could it have been a signal reflected off a piece of space debris, like a discarded satellite booster? Was it a bizarre, one-time-only emission from a passing comet, though the comets proposed were not in the right location at the time? Perhaps it was an extremely rare and intense burst of natural radio emission from an unknown astrophysical object. Every proposed explanation has its own flaws, failing to perfectly account for the signal's unique strength and specificity. It stands as a perfect, tantalizing mystery, a single data point that fuels both our dreams and our skepticism. It is the ultimate cosmic what-if, a brief hello that left us forever wondering who or what might have been on the other end of the line. Far beyond the orbit of Neptune, our solar system does not simply fade into the black. It is home to a vast, donut-shaped swarm of frozen worlds known as the Kuiper Belt, a cosmic junkyard of icy relics left over from the planet's formation. For years, we pictured this region as a gradually thinning cloud of debris, with smaller objects peppering the space all the way out to the Oort cloud. But when astronomers began to map it in detail, they found something deeply strange. The population of these icy bodies does not gently dwindle, it suddenly and dramatically plummets. At about 50 times Earth's distance from the Sun, the Kuiper Belt simply ends, as if it has run into a cosmic wall. This is the Kuiper Cliff, a boundary that defies our basic models of how the solar system was built. If the outer solar system formed from a smooth disk of material, why would the objects just stop at this specific line? The drop-off is so sharp it cannot be explained by the current gravitational influence of Neptune or any other known planet. Something else must be responsible for this stark frontier, one of the most compelling and controversial, theories is that an unseen, massive world is lurking in the darkness. This hypothetical planet 9, with an estimated mass of 5 to 10 times that of Earth, would orbit the Sun on a wildly elongated path far beyond the Kuiper Cliff. Its immense gravity, the theory suggests, would act like a celestial shepherd. Over billions of years, its periodic tugs could have cleared out a vast region of space, either hurling smaller objects into the distant Oort cloud or ejecting them from the solar system entirely. The very emptiness we observe becomes the primary evidence for its existence. Yet, finding this ghost planet is a monumental challenge. Its orbit would be so vast that a single year on Planet 9 could last 20,000 Earth years. We would only see it when its slow path brought it to the correct point in its immense elliptical loop, a needle in a haystack the size of the sky. Other explanations propose that the cliff is a fossil, a frozen record of the solar system's violent infancy. Perhaps the protoplanetary disk from which our planets formed itself had a sharp outer edge, carved by the gravitational influence of a passing star in the Sun's birth cluster. Or maybe the early Sun was born in a dense stellar nursery, and the intense ultraviolet light from a nearby massive star evaporated the lighter ices beyond a certain boundary, preventing larger objects from forming there. The Kuiper Cliff stands as a silent sentinel at the edge of our known domain, a reminder that even our own celestial neighborhood holds profound secrets. Is it the gravitational signature of a hidden world, or is it the scar of a dramatic event from our system's first dawn? Our solar system holds a subtle imperfection, a persistent tilt that has long puzzled astronomers. If you could shrink the entire system down to a dinner plate, you would find that the planets all orbit the Sun in a remarkably flat, thin plane. Yet the Sun itself spins on an axis that is tilted by roughly 6 degrees compared to this planetary disk. It is as if the central gear of a perfect clock is slightly askew. This misalignment is the solar system's quiet tilt, a clue that our cosmic neighborhood was not always this orderly. The leading theory to explain this kink involves a dramatic encounter in the solar system's violent infancy. Picture the Sun surrounded by its newborn protoplanetary disk, a swirling, hot cloud of gas and dust from which the planets were beginning to coalesce. According to this hypothesis, a rogue star passed uncomfortably close to our young system. The gravitational pull from this stellar intruder would have torqued and twisted the entire disk, leaving the Sun's original spin axis slightly misaligned with the new, warped plane of the planets. This was not a catastrophic collision, but a gravitational nudge that permanently set the solar system off kilter. The search for evidence now becomes a cosmic detective story. If such a flyby did occur, it would have left other traces. Astronomers run sophisticated computer simulations, tracing the gravitational dynamics of such an event to see if it can reproduce not just the 6-degree tilt, but also other oddities like the strange, detached orbits of some distant objects in the Kuiper belt. The ultimate goal is to find the culprit itself. By meticulously mapping the motions and origins of the stars around us, astronomers hope to identify a stellar neighbor with a trajectory that can be traced back to a close encounter with our Sun over 4.5 billion years ago. This tilt is more than a geometric curiosity. It is a potential fossil record of a stellar handshake that shaped our cosmic home, a silent witness to the chaotic environment in which every star is born. Our own Sun holds a secret from its youth, a contradiction that threatens to rewrite the story of life's beginnings. Models of stellar evolution are clear. The newborn Sun was a far dimmer star, shining with only about 70% of its current brilliance. With so little energy reaching the inner planets, Earth and Mars should have been frozen solid for their first 2 billion years, locked in a deep global ice age. Yet the geological record tells a completely different story. Ancient rocks on Earth show clear evidence of liquid water, from sedimentary layers to minerals that can only form in wet conditions. Rover missions to Mars have found identical proof, riverbeds and clay minerals that speak of a warm, wet Martian past. This is the faint young sun paradox, a cosmic contradiction where the evidence for habitable conditions stares directly at a model that says it was impossible. How could these worlds have been so warm under such a faint sun? The answer must lie in their ancient atmospheres. Our planet today is wrapped in a thin blanket of nitrogen and oxygen, but its first atmosphere was likely a far thicker, toxic shroud. Scientists propose it was rich in powerful greenhouse gases, molecules like methane and ammonia that are incredibly effective at trapping heat. While carbon dioxide is a well-known greenhouse gas, methane is over 20 times more potent at warming the planet. A dense atmosphere brimming with these gases could have created an intense insulating layer, acting like a celestial parka that kept the early Earth warm despite the weak sunlight. This primordial greenhouse would have been a strange and alien place with skies of orange or brown, but it provided the stable, liquid water essential for the first stirrings of life. Another possibility involves the planet's surface itself. A much younger Earth may have had far less landmass, with darker ocean waters covering a greater percentage of the globe. This darker surface would have absorbed more of the sun's precious light, rather than reflecting it back into space as ice and light-colored rock would do. The true solution likely involves a combination of these factors, a thicker, gassier atmosphere combined with a darker, more absorbent surface, all working in concert to defy the cosmic chill. This paradox forces us to reconsider the delicate balance that makes a world livable. It suggests that planets have their own internal thermostats, feedback systems that can compensate for a star's changing mood. Solving this ancient climate puzzle does more than explain our past. It gives us a crucial key for interpreting the potential climates of exoplanets orbiting other faint stars, expanding our search for life in the cosmos. Even the thin, cold air of Mars holds a secret that refuses to be solved. For decades, our robotic scouts on the red planet have been sniffing the atmosphere, and they keep catching a faint, tantalizing whiff of methane gas. This is not just another scientific reading, it is a profound puzzle. On Earth, the vast majority of methane is produced by living organisms, from microbes to livestock. Its presence on Mars immediately raises the electrifying possibility of life, past or present, lurking beneath the rusty soil. Yet methane can also be created by purely geological processes, like the reaction of water with certain types of rock deep underground. The mystery is not just that we found it, but how it behaves. Unlike the steady, predictable methane in Earth's atmosphere, the Martian methane appears in sudden, sporadic bursts. It will spike to significant levels in a specific location, only to vanish completely just days or weeks later. The Curiosity rover has detected these transient plumes from within Gale crater, while the Trace Gas Orbiter, a European spacecraft circling the planet, has often reported a baffling absence of the gas in the global atmosphere. This erratic behavior is as confusing as it is compelling. If the source were a simple, steady geological seep, we would expect to see a more constant, widespread background level. The fleeting nature of these plumes suggests the methane is being released in sudden, localized pulses and then rapidly destroyed by some unknown process in the harsh Martian environment. Perhaps an intense ultraviolet radiation from the sun is breaking the molecules apart far faster than we anticipate. Or maybe the soil itself is highly reactive, oxidizing the methane the moment it appears. The hunt for the source is a race against time, attempting to pinpoint the origin of a ghostly signature that disappears almost as soon as it is found. Is it coming from subsurface aquifers where ancient microbial life might still cling to existence, producing this gas as a byproduct of its metabolism? Or are we witnessing the slow, abiotic chemistry of water reacting with the mineral olivine in a process called serpentinization, creating methane without any need for biology? Each new detection sends a jolt of excitement through the scientific community, a reminder that the question of life on Mars is not yet closed. Every time a rover drills into a rock or an orbiter scans the horizon, we are not just studying geology, we are following a scent, a whisper on the wind that could lead to one of the greatest discoveries in human history, or to a deeper understanding of a complex and active planet. High above the swirling cloud tops of Saturn, a geometric marvel defies all expectations. At the planet's north pole, a colossal hexagon, wider than 2 Earths, has been spinning for decades, a 6-sided jet stream etched into the atmosphere. This is not a fleeting storm, but a permanent feature, a vast and precise shape standing guard over the pole. Its sides are astonishingly straight, and the entire structure rotates with a period that neatly matches the planet's own radio emissions, a clockwork puzzle set deep within the gas giant. While hurricanes on Earth are circular vortices, this hexagonal monster is a category of weather for which we have no name. The quest to understand it has led physicists back to their laboratories. They have found that when a fluid is spun rapidly in a circular container, smaller, faster vortices can naturally arrange themselves around the perimeter, their boundaries pressing against one another to form straight lines and geometric shapes. In a pan of water, you can briefly see triangles, squares, and even hexagons emerge from the chaos. This suggests the hexagon is a kind of standing wave, a stable pattern born from the shear between different bands of Saturn's raging atmosphere. Yet these lab experiments produce shapes that are tiny and transient, flickering in and out of existence. Saturn's hexagon, by contrast, is a planetary-scale structure of immense stability, enduring for generations without faltering. This is the core of the mystery. Why does this geometric order emerge from the turbulent chaos of a gas giant's atmosphere and then lock into place with such permanence? What is it about Saturn's specific rotation, its internal heat flow, or the depth of its atmosphere that allows this perfect shape to crystallize and hold? The hexagon is more than a curious cloud. It is a natural laboratory testing our deepest understanding of fluid dynamics on a scale we can never hope to replicate. It whispers that even in the riotous weather of a giant planet, there can be an underlying geometry, a hidden order written in the wind. A star located over 1,000 light-years away in the constellation Cygnus performs the strangest dance in the galaxy. Known as Tabby star, it was discovered by the Kepler telescope not for its steady glow, but for its inexplicable episodes of dimming. While a transiting planet might block 1 or 2% of a star's light, this star's brightness would plummet by staggering amounts, sometimes over 20%. These were not the clean, rhythmic dips of an orbiting world, but chaotic, jagged shadows, as if something colossal and irregular were passing in front of it. The data revealed a light curve unlike any other, a signature of pure cosmic chaos. The hunt for an explanation began, and the theories that emerged were as wild as the data itself. The first, more conventional idea was a gigantic swarm of comets. Perhaps a family of icy bodies, shattered by a collision, was trailing immense clouds of dust and debris in a long, eccentric orbit around the star. When this swarm passed between the star and our telescopes, it could, in theory, create the bizarre, deep dimming patterns we observed. Yet, the scale required was almost unbelievable, demanding millions of comets to blot out that much starlight. This pushed scientists toward a far more speculative and thrilling hypothesis. Could we be witnessing the construction of an alien megastructure? The concept of a Dyson sphere, a vast array of energy collecting panels or habitats built by an advanced civilization to encapsulate its star, moved from science fiction into a legitimate, if remote, possibility. The irregular dimming could be explained by a partially completed swarm of these constructs, passing in front of the star in a chaotic, artificial procession. The scientific community responded with a massive observational campaign, pointing every available instrument at this one point of light. What they found was both clarifying and deeply puzzling. Detailed analysis of the starlight revealed that the material causing the dimming was not solid. When the star dimmed, the blue light was blocked more than the red light, a classic signature of fine dust. A solid structure, like a megastructure, would block all colors of light equally. This was a powerful argument against the alien hypothesis, pointing firmly toward a natural cause. But the mystery did not end there. Further studies showed the star is also undergoing a long-term, century-long fading, a slow, steady dimming that compounds the strange, short-term dips. The current best explanation is a complex and ongoing cataclysm. Perhaps a planet was torn apart by the star's gravity, and we are seeing the chaotic aftermath, a vast, disintegrating cloud of rocky debris and dust casting these immense, wandering shadows. Or maybe the star itself is going through a unique and violent phase, belching out immense clouds of soot from its interior. Tabby's star remains a powerful reminder that the universe is capable of phenomena we have not yet dreamed of, and that sometimes the most exciting answer is not aliens, but nature inventing something new and spectacular right before our eyes. In the vast emptiness between stars, a visitor arrived without warning. In October 2017, a telescope in Hawaii detected a faint point of light moving at incredible speed. It was not from our solar system. This was Oumuamua, the first interstellar object ever seen, a messenger from another star. Its trajectory was a hyperbolic arc, a path that meant it was only passing through, never to return. The anomalies began piling up immediately. As it tumbled through space, its brightness varied dramatically, suggesting an extreme, elongated shape, perhaps 10 times longer than it was wide. Nothing in our solar system looks quite like this spinning cosmic cigar. Then came the most baffling clue of all. As Oumuamua hurtled away from the sun, its path could not be explained by gravity alone. It was accelerating as if pushed by an unseen force. For a comet, this is normal, the result of iced gases heating up in sunlight and jetting from the surface, acting like a natural rocket engine. But Oumuamua showed no coma, the classic cloud of gas and dust that surrounds a comet's nucleus. It was starkly barren, with no visible outgassing at all. This left astronomers with a profound puzzle. How could it accelerate without the telltale signs of a comet? The debate ignited, proposing objects we had never before considered. One leading idea suggested it was a cosmic hydrogen iceberg. In the cold depths of interstellar space, a block of solid hydrogen could form. As it neared the sun, the theory goes, the hydrogen would begin to sublimate, turning directly from a solid to a gas, providing the thrust for acceleration without producing any visible dust. The problem is that a hydrogen iceberg is incredibly fragile, likely shattering on its long journey between stars. Another compelling theory posits that Oumuamua was a relic from another planetary system, a chunk of nitrogen ice sheared off from a Pluto-like world orbiting a distant star. This would account for its strange composition and the clean acceleration, as nitrogen sublimation would be difficult to detect. Then, of course, there is the more speculative yet captivating hypothesis from Harvard astronomer Avi Loeb, who suggested it could be a piece of alien technology, a light sail from a long-dead civilization using radiation pressure for propulsion. The scientific consensus, however, leans toward a natural explanation, likely an exotic type of comet from a system with very different formation conditions than our own. The true frustration is that we will never know for sure. Oumuamua is now too far away and too faint to observe further. It was a one-of-a-kind event, a mystery that sailed through our cosmic neighborhood, offered a few tantalizing clues, and then vanished back into the dark. It reminds us that the galaxy is likely filled with such strange travelers, each one a new question waiting to be found. We have charted the cosmos from its darkest secrets to its brightest stars, yet the most fundamental inventory of our own reality remains disturbingly incomplete. While dark matter and dark energy dominate the cosmic budget, even the ordinary matter that makes up you, me, and every star and galaxy we can see is not fully accounted for. This is the mystery of the missing baryons. Baryons are simply the family of particles that include the protons and neutrons forming atomic nuclei, the very stuff of the familiar world. From the pristine conditions of the Big Bang, we can calculate with great precision how much of this ordinary matter should exist in the universe today. Yet when we add up all the stars, galaxies, and the cool gas we can easily detect, we find only about half of what our cosmic ledger demands. So where is the rest of the normal stuff hiding? The leading suspect is not in some distant, exotic realm, but woven into the very fabric of cosmic structure itself. Astronomers believe the missing matter resides in a vast, tenuous web of incredibly hot gas, a ghostly architecture known as the warm-hot intergalactic medium, or WIM. Picture the universe on its largest scales not as a collection of isolated islands, but as a single, interconnected spiderweb. The galaxies and clusters are the dense knots where the threads intersect, and the long, thin filaments stretching between them are the WIM. This gas is so hot, heated to millions of degrees by the gravitational collapse of the cosmic web, that it does not glow in visible light. It is a thin, ionized plasma, nearly invisible to our traditional telescopes. How do you hunt for something that is both everywhere and nowhere, a phantom that permeates the voids between galaxies? The search requires ingenious cosmic detective work. Scientists use distant quasars, the intensely bright cores of active galaxies, as backlighting. As the light from a quasar travels billions of light years to reach us, it passes through these intergalactic filaments. The superheated gas of the WIM absorbs specific, telltale wavelengths of this light, particularly in the high-energy X-ray and ultraviolet parts of the spectrum. It is like looking at a brilliant light through a faint cosmic fog and seeing the specific shadows cast by oxygen atoms that have been stripped of most of their electrons. Finding these absorption lines is like finding the fingerprint of the missing matter. It is painstaking work, requiring the most sensitive space observatories to catch these whispers from the cosmic web. Confirming the existence of the WIM would complete our census of ordinary matter, finally balancing the universe's books. Yet it also reveals a startling truth that most of the normal matter in the cosmos is not locked up in stars or planets, but is drifting in these immense, diffuse reservoirs of scalding gas, a hidden ocean in which the galaxies are merely islands. This growing cosmic confusion has a name, the Hubble tension, and it represents a crack in the very foundation of modern cosmology. For decades, we have worked to measure a single, crucial number, the Hubble constant, which tells us exactly how fast the universe is expanding today. We developed two brilliant, independent methods to pin down this value, and both seemed flawless in their logic. Yet now they are giving us two different, stubbornly incompatible answers. It is as if you used two different, perfectly calibrated rulers to measure the same table and got two different lengths every single time. The first method looks back to the very beginning, to the afterglow of the Big Bang, the cosmic microwave background. By studying the subtle patterns in this ancient light with incredible precision, we can work backwards to predict how the universe should have evolved and what the expansion rate should be right now. This is a top-down approach, starting with the infant universe and running the cosmic film forward. The second method builds the measurement from the ground up, using a cosmic ladder of distance markers within our modern universe. Astronomers use pulsating stars called Cepheid variables, whose intrinsic brightness is tied to their pulse rate as the first crucial rung. By measuring how bright these stars appear from Earth, we can calculate their exact distance. Then we use these Cepheids to calibrate the next rung, the brilliant stellar explosions known as Type 1, a supernova, which are so consistently bright they can be seen across vast cosmic distances. By tracking how these supernovae are receding from us, we get a direct local measurement of the universe's current expansion. The problem is stark. The early universe method, using the cosmic microwave background, gives a slower, more modest expansion rate. The local universe method, using stars and supernova, gives a faster, more frenetic one. The discrepancy is not large, only a few percent, but it is far greater than the tiny error bars on either measurement. This is not a mistake, it is a mismatch. This tension suggests that something is missing from our cosmic model. Perhaps dark energy is not constant, but has been growing stronger over time, giving the modern universe an unexpected extra push. Or maybe dark matter possesses properties we have not yet imagined, interacting with itself or with light in strange new ways. There is even the thrilling possibility that the universe contains additional, unknown types of subatomic particles that flooded the early cosmos and altered its expansion history. Every new observation, every more precise measurement of Cepheid stars or the cosmic microwave background tightens the screws on this puzzle. The Hubble tension is not a failure of science but a signpost. It is the universe telling us that our otherwise successful model of cosmology is incomplete, and that we are on the verge of discovering something profoundly new about the fabric of reality. Streaking through the void are bullets of pure energy, subatomic particles moving at a fraction of the speed of light and carrying more punch than a major league fastball. These are ultra-high energy cosmic rays, and their existence is a profound assault on the laws of physics. A single one of these particles, often a lone proton or atomic nucleus, can possess the energy of a falling brick, all compressed into a speck smaller than an atom. They are millions of times more powerful than anything we can produce in our greatest particle colliders. The mystery is not just their incredible energy, but their origin. Where in the cosmos is the natural particle accelerator capable of such a feat? Tracing them back to their source is a cosmic nightmare. Because these particles are electrically charged, their paths are scrambled by the magnetic fields that permeate interstellar and intergalactic space. Imagine trying to trace a single, twisted raindrop back to a specific cloud during a hurricane. By the time one of these cosmic bullets slams into Earth's upper atmosphere, creating a vast shower of secondary particles, its original direction is completely lost. We know it came from somewhere out there, but the map is a hopeless jumble. The hunt forces us to consider the most violent engines in the universe. The leading suspects are active galactic nuclei, where supermassive black holes at the hearts of galaxies devour matter and spew out colossal jets of radiation and plasma. These jets could act as unimaginable particle accelerators, boosting matter to near light speed over vast distances. Another potential culprit is the gamma-ray burst, the single most energetic explosion since the Big Bang, which could blast out a shotgun spray of ultra-high energy particles as a dying star collapses into a black hole. Some theories even point to the chaotic mergers of galaxy clusters, where shocks rippling through the intergalactic gas could provide the necessary kick. The challenge is to catch enough of these rare particles and use the entire planet as a detector. Observatories like the Pierre Auger Array in Argentina use thousands of water tanks spread over 3,000 square kilometers, waiting for the faint ripple of a particle cascade. Each hit is a data point, and slowly a statistical map is emerging. Is the answer a single, unimaginably powerful source, or a chorus of cosmic catastrophes scattered across the sky? These particles are messengers from the most extreme environments in existence, and they are challenging us to decipher their violent origins. The universe's ultimate destiny hinges on a single, invisible actor, the same dark energy currently accelerating its expansion. This mysterious force does not just dictate the present pace of the cosmos, it writes the final chapter. Scientists have envisioned 3 primary endings for this epic story, each one determined by the density of the universe and the true, unchanging nature of that dark energy. The first scenario is the Big Crunch, a dramatic reversal of the Big Bang itself. In this vision, the density of matter and energy in the cosmos is just high enough that gravity eventually overcomes the outward push of dark energy. The expansion would slow to a halt, and then the universe would begin to collapse in on itself. Galaxies would rush together, the background temperature of space would soar, and all structures would be torn apart in a fiery descent toward a single point, a singularity of unimaginable heat and density. It is a cosmic rebirth through total destruction. The second, and currently most favored, scenario is far more bleak and lonely. Known as the heat death or the big freeze, this future unfolds if dark energy remains a constant force and the universe continues to expand and thin out forever. In this slow, cold end, stars will one by one burn through their fuel and wink out. Galaxies will fade to black. Even the massive black holes at their centers will, over trillions upon trillions of years, evaporate away through a quantum process known as Hawking radiation. The universe will approach a state of absolute equilibrium, where the temperature is uniform everywhere and no energy can be transferred to do any work. It becomes a cosmic graveyard, an eternal, dark, and lifeless void where even time loses its meaning. The third possibility is the most violent and abrupt of all, the Big Rip. This terrifying finale depends on dark energy not being constant, but instead growing stronger over time. If this repulsive force, which scientists call phantom energy, continues to intensify, it would eventually overcome every force that holds things together. First, galaxy clusters would be torn apart, then individual galaxies. As the acceleration becomes infinite, gravity would be powerless to hold stars in their orbits. In the final moments, planets would be shredded from their suns, and atoms themselves would be ripped apart, their nuclei torn from their electrons. The very fabric of space-time would be sundered. The choice between these fates rests entirely on the properties of the dark energy we still do not understand. Is its push constant, or is it getting stronger? The answer is hidden in the evolving expansion rate, a secret we are slowly teasing out with every new telescope and deep space observation. Our cosmos is on a one-way journey, and we are only just beginning to read the map that will tell us where that road ultimately leads. Deep within the heart of a black hole lies a paradox that threatens to shatter our understanding of reality itself. Stephen Hawking made a startling prediction that black holes are not entirely black. Through quantum processes at their very edge, the event horizon, they slowly leak radiation and evaporate over astronomical timescales. This Hawking radiation, however, carries a terrifying implication. It appears to be completely random, bearing no trace of the information about what fell in. A book, a star, or an entire civilization swallowed by the black hole would all be reduced to the same featureless thermal glow. When the black hole finally vanishes, all that unique information seems to be erased from the universe forever. This is the black hole information paradox, and it creates an irreconcilable war between the two pillars of modern physics. General relativity, which governs gravity and the large-scale structure of spacetime, insists that what crosses the event horizon is gone for good. Yet quantum mechanics, the rulebook for the small, has a sacred, unbreakable law. Information cannot be truly destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. Hawking's discovery suggested that black holes violate this most fundamental quantum principle, forcing physicists to choose between their two most successful theories. The search for a solution has led to some of the most mind-bending ideas in all of science. One radical proposal is the holographic principle. It suggests that all the information describing the three-dimensional volume inside a black hole is actually encoded on its two-dimensional surface, the event horizon, like a cosmic fingerprint. The information was never truly inside the black hole to be lost. It was always smeared across its boundary, and it might slowly leak back out in the Hawking radiation in an incredibly scrambled, complex code. Another startling idea is the firewall hypothesis. If information is to be preserved, it might require a violent rewrite of the rules at the event horizon. Instead of an invisible boundary you could cross unnoticed, the event horizon could be a searing wall of high-energy particles, a literal firewall that would instantly incinerate anything falling in. This solves the information puzzle by dramatically destroying the infalling object at the horizon, but it violates Einstein's principle that free fall should feel like floating in empty space. We are left with a cosmic catch-22, where saving quantum information seems to require setting the sky on fire. This paradox forces us to confront the fact that our theories of the very large and the very small are fundamentally incompatible. The fate of information falling into a black hole is the ultimate testing ground, a place where our current laws of physics break down and where the next great revolution in our understanding of the universe must be born. The smooth, continuous fabric of spacetime, as painted by Einstein's theory, may be our most beautiful illusion. At the very smallest scales, the universe might be digital, a seething foam of discrete grains. This is the profound challenge of unifying general relativity with quantum mechanics, a clash of titans that has defined theoretical physics for a century. One tells us that space and time are a dynamic stage warped by mass and energy. The other reveals that the actors on that stage, all matter and force, are fundamentally quantized, existing in tiny, indivisible packets. The stage itself, however, remains stubbornly continuous in our equations. It is as if we have a perfect theory for the ocean's waves and a perfect theory for the water molecules, but no way to describe the frothing, chaotic foam where they meet. To resolve this, we must find the atoms of space and time. One leading candidate is loop quantum gravity. This theory proposes that space is not a smooth backdrop, but is woven from a network of incredibly fine, one-dimensional loops. Picture the fabric of your shirt, which seems continuous until you look closely and see the individual threads. In this view, these threads of space intersect to form a spin network, and the tiny areas and volumes they enclose can only take on specific quantized values. There is no such thing as a length smaller than the Planck length, a fundamental unit of distance. Time, too, would advance in these tiny, discrete steps like the individual frames of a cosmic film. Another grand contender is string theory, which takes a dramatically different approach. It suggests that the fundamental entities are not point-like particles but unimaginably small, vibrating strings. The different vibrational patterns of these strings give rise to all the particles and forces we observe. Crucially, string theory requires more than the three spatial dimensions we experience, proposing extra, curled-up dimensions that are too small for us to perceive. In this framework, gravity emerges naturally from a specific string vibration, and spacetime itself is a secondary structure born from the collective behavior of these strings. The immense challenge with all these theories is putting them to the test. The energy scales required to probe these fundamental grains of spacetime are far beyond anything our particle colliders can ever achieve. We are searching for effects so subtle they are like trying to measure the width of a human hair from a distance of 1,000 light-years. Some hope rests on indirect evidence, perhaps from the faint imprint of the early universe on the cosmic microwave background, or from the gravitational waves generated by the most violent cosmic collisions. Until then, we are navigating by mathematical beauty alone, searching for a key to a lock we cannot yet see, driven by the conviction that the universe must be unified at its core. The leap from chemistry to biology is perhaps the most significant transition in the history of our planet. In the early Earth's chaotic environment, a collection of non-living molecules somehow crossed a profound threshold and began to replicate, to metabolize, to become alive. The exact recipe for this genesis remains one of science's ultimate black boxes. Was it a lightning strike in a primordial soup, as the famous Miller-Urey experiment suggested? Did the first sparks of life ignite in the scalding, mineral-rich vents at the bottom of the ocean, protected from a hostile surface? Or did the essential building blocks, the amino acids and sugars, arrive ready-made from the cosmos, delivered by comets and meteorites that bombarded our young world? This is not just a question about our past, but about our cosmic context. If life emerged so readily here, it should be common across the galaxy. If it was an astronomically rare fluke, then our planet may be a solitary oasis of meaning in a vast sterile desert. This uncertainty leads to a fascinating possibility, the concept of panspermia. What if life does not have to start from scratch on every new world? Panspermia is the hypothesis that microbial life, incredibly hardy and dormant, could be transported from one planet to another, hitching a ride inside rocks blasted into space by asteroid impact. We know that pieces of Mars have landed on Earth as meteorites, and the reverse is also true. If tiny organisms could survive the violent ejection, the long, cold journey through interstellar space, and the fiery descent through a new atmosphere, then life could be a cosmic contagion, seeding entire star systems. The discovery of thousands of exoplanets, many orbiting within their star's habitable zone where liquid water could exist, has transformed this speculation into a pressing line of inquiry. With so many potential incubators, the silence from the cosmos grows ever more puzzling. Are we the first, are we the last, or are we simply one voice in a galactic chorus we have not yet learned to hear? The origin of life is the mystery that connects the cold laws of physics to the warm, messy reality of our own existence, and its solution will redefine our place in the universe. Our galaxy is not drifting aimlessly through the cosmos, but is being pulled by a force of unimaginable scale. This is the Great Attractor, a gravitational monster lurking in the depths of intergalactic space, tugging not only on the Milky Way but on an entire swarm of galaxies, all flowing in a silent, cosmic river toward an unseen destination. The sheer power required to command the motion of thousands of galaxies points to a concentration of mass so colossal it defies easy comprehension, a gravitational heart for our local corner of the universe. Yet for decades, this titan remained a ghost, its core hidden from our view by a cosmic curtain. This region of the sky lies in the direction of the constellation Centaurus, but it is directly behind the crowded, dusty plain of our own Milky Way. Astronomers call this the zone of avoidance, where the light from beyond is swallowed by countless stars and opaque clouds of cosmic dust, rendering traditional optical telescopes nearly blind. It was like trying to see a distant mountain range through a thick, perpetual fog. The breakthrough came when we learned to see the universe in new light. By deploying space-based telescopes sensitive to X-rays and infrared radiation, we could peer through the obscuring veil. X-rays punch through the dust, revealing the hot, energetic gas that often surrounds massive galaxy clusters, while infrared light penetrates the murk to show the faint glow of stars themselves. What these new eyes revealed was not one single, monolithic structure, but a complex tapestry of mass. The original Great Attractor appears to be part of a much larger cosmic flow, a vast river of galaxies all being drawn toward an even more immense concentration of mass known as the Shapley supercluster, the largest such structure in our local universe. The Great Attractor itself is now understood as a major knot in the cosmic web, a dense supercluster of galaxies whose combined gravity creates this powerful pull. We are essentially caught in a slow-motion cosmic tide, riding a current set in motion by the uneven distribution of matter billions of years ago. This hidden giant reminds us that the true architecture of the cosmos is often invisible, written not in starlight but in the relentless, silent pull of gravity. The universe is not just a collection of galaxies but a tapestry of profound emptiness. Scattered across the cosmos are regions of near-total nothingness, voids so immense they defy our understanding of how matter should be distributed. The most famous of these is the Boötes Void, a spherical chasm of space so vast it could contain thousands of galaxies, yet holds only a handful. If our Milky Way sat at its center, we might not have discovered other galaxies until the 1960s, our sky a dark and lonely expanse. These cosmic deserts are not mere accidents, they are fundamental features of the universe's large-scale structure, the flip side of the dense clusters and filaments that make up the cosmic web. Their existence is expected, but their staggering size is not. How could a void grow to be hundreds of millions of light years across, a bubble of almost pure vacuum in a universe that should be more evenly mixed? The leading theory points back to the very first moments of time. Tiny quantum fluctuations in the infant universe, imprinted on the cosmic microwave background, were the seeds for all future structure. Regions that were slightly less dense than average began to expand faster than their surroundings, as their weaker gravity could not pull matter inward. Over billions of years, these underdense regions stretched and merged, emptying out as galaxies were gravitationally swept toward the denser walls and nodes of the cosmic web. It is a cosmic rich get richer, poor get poorer scenario on an unimaginable scale. Yet the sheer scale of the Boötes void pushes this model to its limits. Is its existence a statistical fluke, a single, extraordinary roll of the cosmic dice? Or does its presence and the distribution of other giant voids hint at something deeper? Perhaps the repulsive force of dark energy plays a role, not just accelerating the overall expansion, but actively helping to inflate these empty bubbles, stretching the fabric of space within them faster than anywhere else. These great voids are more than just empty space. They are dynamic entities, their growth and evolution offering a unique probe into the forces that shape our cosmos. By mapping their sizes and distribution, we are reading a history of the universe written in negative space, a silent testament to the tug of war between gravity and dark energy that has been raging since the dawn of time. What if everything you know, this entire universe with its galaxies and atoms and the very air you breathe, is not the base reality but an elaborate digital construction? This is the simulation hypothesis, a philosophical argument that suggests our existence might be a sophisticated simulation running on a computer of unimaginable power. The idea, once confined to science fiction, has gained serious traction among technologists and physicists. The core argument often begins with a simple logical progression. If a civilization can reach a post-human level of technological maturity, it is reasonable to assume it would possess the computational resources to run vast, detailed simulations of its own history or of entirely fictional worlds. And if such a civilization ran even a large number of these simulations, the number of simulated minds would vastly outnumber the one original biological reality. Therefore, statistically, it is more likely that we are among the simulated beings than the original ones. It is a cosmic numbers game, and the odds are not in our favor. The argument gains further weight from the nature of our own universe. The physical laws that govern reality are fundamentally mathematical. They can be written down as elegant equations, and they operate with a precision that feels more like computer code than anything else. The universe appears to be quantized, with space, time, and energy all coming in discrete, indivisible packets, much like the pixels on a screen or the bits in a computer. This pixelation of reality at the Planck scale could be seen as evidence of a finite resolution, a necessary feature of any simulation to conserve processing power. Even the strange rules of quantum mechanics, where particles exist in a haze of probability until observed, could be interpreted as a rendering optimization, a way for the simulation to only calculate the precise details of a system when someone is actually looking. Yet, compelling counterarguments exist. The sheer energy and computational requirement to simulate every particle in a universe, let alone the consciousness of every being within it, seems impossibly vast. Perhaps such a project would violate fundamental thermodynamic laws, making it physically impossible even for a godlike civilization. Furthermore, if our universe is a simulation, we might expect to find glitches or shortcuts in the code. Some have suggested that the bizarre behavior of particles in quantum experiments could be one such artifact. Others look for potential limits in the fabric of spacetime itself, like evidence that the cosmic speed limit, the speed of light, is a processing limit on information transfer within the simulation. The search for evidence is a frontier of its own. Could a high-energy cosmic ray be a data error, a bit flip in the cosmic processor? Or might we one day discover a mathematical signature in the laws of physics, an Easter egg left by the programmers? The simulation hypothesis forces us to confront the deepest questions of existence, consciousness, and reality itself. Whether we are in a base reality or a grand simulation, the cosmos we perceive remains our home, filled with wonders that are no less real for being potentially coded. It is the ultimate mystery, one that may forever linger at the edge of proof, challenging not just what we know, but the very nature of knowing. From the ghostly pull of dark matter to the silent scream of the wow signal, this journey through 25 cosmic enigmas reveals a universe far stranger than we ever dreamed. We have explored puzzles that challenge the very laws of physics, from the information paradox in black holes to the unsettling tilt of our own solar system. Each mystery is a reminder that our knowledge is a tiny island in a vast ocean of the unknown. The pursuit of these answers is not a sign of failure, but the very engine of discovery, pushing our instruments and our imaginations to their absolute limits. Every unexplained signal and every anomalous measurement is an invitation to look deeper and think bigger. We stand at the frontier, peering into the dark, driven by an insatiable curiosity about our place in the cosmos. So we turn the question to you. After this incredible journey, which of these 25 mysteries captures your imagination the most? Is it the hunt for Planet 9, the true nature of dark energy, or the profound silence of the Fermi paradox? Let us know in the comments below, and if you are hungry for more deep dives into the wonders of space, be sure to subscribe. The universe still has countless secrets left to tell.